Teacher Earl, and welcome to Grade 10 Mathematics. A Student's Guide to Learning from Home. Set up your study space. Find an area in your house where you can sit comfortably and focus. Take down notes. Plan your day ahead. If you have one, follow the schedule provided by the school. Lesson distractions. Lock your phone away or turn it off. Change it up. Take breaks in between. Let your mind rest and recharge. Speak and ask for help. When things get through or tough, don't push it. Write it down using a journal or a notebook. Learning from home can be difficult, but it's definitely achievable. Module 1 is entitled Generating Patterns. It consists of 2 lessons, Lesson 1, Finding the Terms of a Sequence, and Lesson 2, Finding the nth term of a sequence. So, patterns are generally found in any form, or it can be found in nature. It can also be simple clothing or fabric, the one that you usually wear, your checkered polo shirts or your stripes top. Okay, so it is already a pattern of colors. Patterns can also be found in objects or in shapes, like these triangles here. And of course, patterns can be found in numbers. So those or that specific pattern there would be our focus, the pattern in numbers. So those patterns in numbers can also be referred to as sequences. So a sequence is a set of numbers in which the next term can be predicted from the previous terms. So what are those terms? The term that we are using here is not the layman's term that we know. The term is merely the count of each and every element found in a certain sequence. So suppose we have the sequence 1, 5, 9, 13, and 17. So there we have 5 terms because we have 5 elements, okay, or 5 entries of numbers. So that 1 there is called the first term, or A1. That 5 there is called the second term. 9 is the third term, and then 13 is the fourth term, and 17 is the fifth term. Each term of a sequence can be represented as follows. And again, the letter that we are going to use for term is A. Now, here, I will show you, of course, the same. This is just a very basic concept, but I want you to know about subscripts. So, our terms is written this way. Say we have the first term, or A1. A is the base, and here the tiny little number beside A, or on the lower right portion of A, is called the subscript. That's why we can have, or we can read this one as A sub 1, because 1 is a subscript of A. And also, but here in our discussion, I will just read this for you as A1. Okay, so for the terms of a sequence, A1 represents the first term, A2 represents the second term, A3 represents the third, and so on. And then AN represents the nth term, or the last term of the sequence. A sequence is a function whose domain is the finite set, which contains 1, 2, 3, and so on up to a certain number n, or the infinite set, which contains 1, 2, 3, and so on and so forth. For instance, we have sequence A versus sequence B. So sequence A consists of the elements 10, 12, 14, 16, and 18. That sequence there is a finite sequence since it has a last term, which is 18. Meanwhile, sequence B, which contains the same set of numbers 10, 12, 14, 16, and 18, but with this three dots right after 18, that means that the sequence B that we have here has no last term, which means it continues infinitely, or after 18 we still have a lot of numbers, say 20, 22, 24. We can even reach up to millions of numbers, okay? More examples on infinite versus finite sequences. So let us be reminded again that infinite sequences are sequences that has no last term, and finite sequence is a sequence which contain a last term. So if the example goes set of counting numbers, then you can just have 1, 2, 3, 4, 5, 6, 7, 8, and so on. So you can write 1, 2, 3, 4, 5, comma, dot, 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 which denotes that your set of counting numbers goes on infinitely. Okay? Next, the set of counting numbers up to 5. This time, this is a finite sequence. Since we have a limit up to which number are we gonna stop. So the the set of counting numbers up to 5 are only 1, 2, 3, 4, and 5. That's just it. Next, suppose we have the set containing 5, 10, 15, 20, 25, and so on and so forth. Okay, that means that this sequence here is an infinite sequence. Okay, we can have the next term as after 25, we can have 30, 35, 45, 50, and so on. You can even have 1,000,005 for it. And then that number is not yet the last term, okay? So again, those numbers that are those sequences that has no last term or that goes on forever is an infinite sequence. Another example here for finite. While for finite we have 5, 10, 15, 20, and up to 25 only. So that's finite. Next, suppose you're going to obtain the set of odd numbers divisible by 5. So remember that odd numbers in our vernacular, that is bungkig, and even numbers in our vernacular, that is pares. So bungkig and divisible by 5. So numbers that are odd that can be divided by 5. So we have 5, 15, 25, 35, and so on and so forth. Here after 35 we can still have 45, 55, up to. Okay, so that is an infinite sequence. Next, for the while in the finite sequence column, we have the set of numbers from 2 to 10. So we have a limit here, and the set that we have is only 2, 4, 6, 8, up to 10 only. So again, when it is limited, when it has no last term, that is a finite sequence. But if it is unlimited, if it goes on forever, if your sequence does not stop, it has a really wide variation, and also it has those three dots that denote so on and so forth, that is an infinite sequence. I hope it is clear to you. I hope you understand the difference between them, between the infinite and the finite sequence. Okay, let's answer first the preliminary activity, guess the missing term. Number 1, we have A, C, E, G. So observe that these four here are just letters of the English alphabet, skipping one letter at a time. So we have A, B is skipped, C, D is skipped, E, F is skipped, we have G, H is skipped, and then I, J is skipped, we have K, and then L is skipped, and then we have M. So we have A, C, E, G, I, K, M. Number 2, we have 2, 4, 6, 8. The next three terms here are very obvious. These are just the even numbers. Okay, so we have 2, 4, 6, 8. Of course, the next one is 10. We have 12, and we have 14. Another way also is by adding 2 in every term. So we have 2 plus 2 is 4, plus 2 is 6, plus 2 is 8, plus 2 is 10, and so on. Okay, we have the same answer, 10, 12, and 14. For number 3, we have 5, 15, 25, 35. So what can you observe from these first 4 numbers of our sequence? So observe that each of the term is added 10 from the preceding one, or from the term before it. So to obtain 15, we have to add 5 by 10. To obtain 25, we have to add 15 by 10. And to obtain 35, we have to add 25 by 10. So it's just 5 plus 10 plus 10 plus 10 and so on. So the next one after 35 is just 45, plus 10 we have 55, and then plus 10 we have 65. That's it. For the next one, suppose we have 1, 1, 2, 3, 5, 8. This is a little different from the patterns that we had. Observe here that the two terms, when added, will result to the next term. Or when the two preceding terms is added, that will result to the next term. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 5 plus 8 is 13. And then 13 plus 8 is 21. 21 plus 13 is 34. And by the way, this is the Fibonacci sequence. Easy for number 4. Next, number 5. So suppose we have 10, 100, 1000, 10,000. What would be the next term, or the missing term? There are two ways here. We can add 0. So the first term, which is 10, has only one 0. The second term, which is 100, has 2 zeros. The third term, which is 1000, has 3 zeros, and so on. So the fifth term is also following the same pattern. The fifth term has 5 zeros, and the answer is 100,000. Another way to solve this one is for you to multiply the first term by 10. Okay, so we have 10 times 10 is 100. 100 times 10 is 1000. 1000 times 10 is 10,000. And 10,000 times 10 is 100,000. So whichever way or whichever process you choose, you'll still have the same answer basically. So you just observe the pattern and just provide the missing term. Alright, so for you to understand sequences better, we are going to cite examples and with, of course, solutions. As we go along with our examples and with the solutions as well, I want you to get your notebooks and or any scratch paper so that you can scribe and solve it along with me as we go through with this with the process of answering our solutions. Okay, so for example 1, suppose we are going to write the first 5 terms of the sequence whose nth term is given by an is equal to 2n plus 1. So our solution here comes off with the substitution process. So we are just going to substitute the value of n for each term. So here, since we are going to solve, of course, for the first 5 terms, then the unknowns were a1, a2, a3, a4 up to a5. So of course, use the main formula or main equation from the example itself. So we have an is equal to 2n plus 1. The variable that we're going to change here, to substitute here, is n. So our first n would be 1, of course. So we have a1 is equal to 2 times 1 plus 1. Then simplify. In simplification, you are just going to multiply the, of course, follow MDAS. Multiply first 2 and 1, and then after that, you're going to add it to 1. Okay, so we have 2 times 1 is 2, plus 1, we have 3. Thus, 3 is our first answer, or that is our A1. Next, for A2, substitute 2 for n. So we have a2 is equal to 2 times 2 plus 1. And that is, of course, 2 times 2 is 4, plus 1 is just 5. And then the same procedure would go through after solving it. So for a3, a4, and a5. So the same procedure to just multiply first. So we have 2 times 3 plus 1 is 7. For a4, we have 2 times 4 plus 1 is 9. And for a5, we have 2 times 5 plus 1 is 11. Okay, so after solving for a1, a2, a3 up to a5, we are then going to write these answers 3 up to 11 in a sequence manner with a comma in between them. Okay, so therefore, the first 5 terms of the sequence is 3, 5, 7, 9, and 11. Next, we'll have example 2. So suppose we're going to write the first 4 terms of the sequence whose nth term is given by an is equal to 4n minus 5. After getting the first 4 terms, we are then going to solve for its 50th term. So here we have a different challenge, no? It's a little harder, but if we try to move along with it, you just follow the process here, and I'm sure you will be familiarized with the solutions. So again, substitute the right value of n for each term. So since we're going to solve for the first 4 terms first, so the first n values that we will have is 1, 2, 3, and 4. And for the 50th term, the n value is 50. So following the formula or the equation an is equal to 4n minus 5. Using n as our first value, so we have a1 is equal to 4 times 1 minus 5. And then solve. 4 times 1 is just 4. 4 minus 5 is negative 1. Next, for 2. So suppose we have a2 is equal to 4 times 2 minus 5. So 4 times 2 here is 8. 8 minus 5 is 3. So our a2 is equal to 3. Next, for a3, we have 4 times 3 minus 5. So 4 times 3 here is 12. And 12 minus 5 is 7. Next, for a4, so we have 4 times 4, that is 16. And 16 minus 5 is 11. Next, for a50, since we're done with a1 to a4, we're going to solve for a50. So the same procedure, you are going to substitute for n. So this time, our n is 50. So we have a50 is equal to 4 times 50 minus 5. 4 times 50 is of course 200. And 200 minus 5 is 195. So therefore, the first 4 terms of the sequence is negative 1. We have 3, 7, and 11. And the 50th term is 195. So that's just it. After you solve for the values of a1, a2, a3, and whatever terms of the sequence that is unknown, you just write it in a sequence manner, writing the number, comma, next number, comma, and so on. Okay, so let's proceed to example 3. What is the 10th term of the sequence defined by the formula an is equal to n squared plus n minus 1? This time we have a quadratic equation of degree 2. So no matter how hard the equation is, because it depends. Some of the items has easier equations or easier formulas, while some has complicated ones. So all you have to remember and to focus is that you are going to get the right number of n and then substitute it from the main equation and then simplify it. That's just it. Okay, so here from our example 3, the unknown is the 10th term, so the n that we are going to use is 10. So from the main equation, we have an is equal to n squared plus n minus 1. And then we are going to substitute 10 for every n. So we have a10 is equal to 10 squared plus 10 minus 1. Now I want you to recall the concepts on exponents in case you have forgotten. So If we have a squared, just like this one, say we have 10 squared, it means that we are going to multiply 10 by itself and not to 2. Okay, so for instance, if we have 4 squared, that means that we're going to multiply 4 times 4. That will result to 16. And if we have 10 squared, that means we're going to have 10 times 10, which is 100. Okay, moving on. So we have there 10 squared, which is equal to 100, plus 10 minus 1. So you just add and then subtract. So 100 plus 10 is 110, minus 1 is 109. So we only have one answer from this question, since the only unknown value here is the 10th term. So that's just it. Our answer is 109.